Hello, everyone. This is Stephen Massa with the Water Environment Federation. I want to welcome each of you to the Carbon and Resin Solutions for PFAS Removal e-Showcase. Before we begin, I would like to quickly review a few logistics. During this webcast, while you cannot speak directly to the presenters, you will have an opportunity to submit questions by typing your specific question into the GoToWebinar pane that appears on the right-hand side of your computer screen. We will be accumulating questions and will direct them to the presenters at the end. The PDF PowerPoint presentations are now available for downloading at WEF's website and are currently available in the Handouts pane of the GoToWebinar panel. This link was included in the GoToWebinar reminder email sent an hour before the webcast and will be included in the follow-up email sent 24 hours after the webcast has ended. We will be recording this e-showcase. The recording link will be available on the webcast website 24 hours after the webcast has ended. TDH credits are not available for this event. Please note that today's event is an e-showcase and does not necessarily reflect the views of the Water Environment Federation. If you have any additional questions after the webcast has ended, please email webcasts@wef.org. Our first speaker today will be John Lombardo. John is a product manager at Evoqua. John, I'll hand it over to you.
Thank you, Stephen. Hello and good day, everyone. Thank you for joining this webinar on carbon and resin solutions for PFAS removal. My name is John Lombardo, and I am Product Manager for Evoqua Water Technologies Environmental Solutions Division. Representing Evoqua on today's webinar will be Caitlin Beretta, Technical Business Development Manager for the East, Adam Redding, Scientist, Activated Carbon Technologies, Kathy Swanson, Technical Business Development Manager for the West, and Tom Malman, Scientist, Resin and Ion Exchange Technologies. The agenda for today's webinar is PFAS overview, treatment options for PFAS, granular activated carbon for PFAS treatment, anion exchange for PFAS treatment, and we will close with an online Q&A session. Our first presenter is Caitlin Beretta, Technical Business Development Manager for the East. Caitlin?
Thanks, John. Hello, everyone. As John mentioned, I'm Caitlin Beretta. I'm the Business Development Manager for Evoqua, and I'm going to start off with an overview of PFAS. So PFAS stands for per and polyfluoroalkyl substances. It represents a class of synthetic chemicals that are manufactured to make products either stain or heat or water resistant. They're also used to suppress fires and firefighting foams. They're used ubiquitously across many industries and products. They're probably located in the shirt you're wearing or the chair you're sitting in or even the carpeting on the floor of the room you're in. As you can see on the right, they're also used in food wrappers and Teflon pans. They're very widely used. On the left-hand side of the screen, you'll see two different types of PFAS chemicals that are well known, PFOA and PFOS. And the reason they're well known is because they were specifically called out in the EPA's health advisory limit that came out nearly 2 years ago now. And one of the common threads you'll see here is that both of them have a very frequent carbon-fluorine bond. And that is the strongest bond in chemistry, so it really speaks to its stability. So when you pair its widespread use in products, as you can see on the right-hand side, with its strong stability on the left-hand side, you can see how that amounts to a large environmental problem. So let's take a look at a larger snapshot of the PFAS chemicals. You'll see I've highlighted on the screen PFOA and PFOS, the two chemicals that we just discussed on the last slide. We actually offered a webinar last year that focused specifically on PFOA and PFOS. And since then, through our research, we've really learned a lot about how there's a much larger suite of chemicals that pose a human health threat. We've also learned that the chemicals that you see here on the screen and many more have different affinities for treatment as well. And there are two things that in particular in regarding trends for treatment that we've learned. The first is that carbon chain length makes a difference in the fact that the longer the chain or the higher the molecular weight, the easier it is to remove these chemicals. The second is that as you can see, each of these chemicals have a carbon backbone with a functional group on the end, and that functional group is going to make a difference in treatment as well. The left-hand side includes some carboxylic acids, and the right-hand side includes some sulfonic acids, and what we've seen in our research is that the sulfonic acids tend to be a little easier to remove as well. So why now? We've talked about the EPA's health advisory that came out 2 years ago. And while that's non-enforceable, public perception has really driven a lot of water authorities and military sites to take action now. As you can see on the map, there's also the green states, which have moved forward with their own standards or guidances for PFAS. And oftentimes they've included PFAS chains that are both short and long, not just meeting the EPA's health advisory standard. And we would certainly expect that a lot more states will follow suit in the next 3 years, three or more years or so. So this slide shows the most commonly used treatment methods for PFAS removal. So starting on the right-hand side, we have membranes. And for membranes, they're highly effective at removing a wide range of PFAS, and they'll also remove any dissolved solids in the water as well. But it is important to keep in mind that they do have a higher capital cost, and they are going to produce a liquid waste stream that would then need to be managed. So moving left, our main focus today is going to be on GAC, or granular activated carbon, and single pass ion exchange. And it's our focus today because all of our full-scale operations thus far, in terms of media and equipment, have involved GAC or ion exchange across the US. So starting with granular activated carbon, GAC thus far is the most proven technology in the fact that it has the most full-scale installations thus far. It not only removes PFAS, but also will remove other organic contaminants in the water. But it is important to keep your finger on the TOC, or total organic carbon content, in the water, as that will compete with the PFAS absorption. Moving into single pass ion exchange, this technology has been validated in the field, and we have some great data to show later in the presentation. This requires a lower empty bed contact time, which translates to a small footprint. So if footprint is an issue, this is a technology to look at. And we have seen high throughput. It is also important to keep in mind that with single pass ion exchange, once it is spent, it will need to be either landfilled or incinerated. So as I mentioned before, the suite of PFAS chemicals are, they need to be treated differently, and every water is going to be different. And as you can see on the bottom of this slide, Evoqua does offer products and solutions for each of these three categories. So when you compare that with our expertise, we're here and ready to help you to find the right solution for your water and treatment goals. So now I'd like to specifically talk about GAC in more detail. GAC is a highly porous media that can treat both air and water streams, or liquid streams for that matter. It can be created from any carbonaceous feedstock, but some of the most common sources are located in the bottom right-hand corner, and that includes coconut shells or various ranks of coal and wood. And actually that product, once it's activated, is so porous that if you had a spoonful of it, the internal surface area of that spoonful of GAC would be enough to cover an entire football field. Now, of course, performance of each of these different carbons is going to vary and can be tailored for certain applications as well. And that really comes down to two main parameters. That's porosity and surface chemistry. Surface chemistry for carbons used in water treatment are for the most part similar because they're all steam activated. So really the main parameter when you're looking at performance differences comes down to porosity. So it's important in water treatment. So to further illustrate the importance of porosity, let's take a look at the graph on the right. The graph compares three different types of carbons: bituminous, virgin coconut, and enhanced coconut in regards to their relative porosity. The left-hand side of the screen shows the relative amount of micropores, or the smallest pores, and the right-hand side shows the relative amount of mesopores, or the medium-sized pores. Ideally, a carbon with high performance would have a good balance of both of these. To use an example, micropores can be analogous to parking lots, and mesopores can be analogous to highways, whereas the cars are the contaminants. So if you have a large parking lot with not very many roads to get those cars there, you're going to have a lot of impaired diffusion or traffic. If you have a parking lot with many roads to get there, you're going to have a much better transport rate and a higher performance of that carbon overall. And as you can see on this graph, the enhanced coconut product has a good amount of both types of pore sizes compared to the other feedstocks. And this is a patented product that we call AquaCarb CX. So this next slide gets into Evoqua's GAC products for PFAS removal. We've just talked about the AquaCarb CX product, which is our enhanced coconut GAC. But we also offer our UltraCarb 1240AW, which is a subbituminous-based coal product. As I mentioned, both of these products have optimized porosity for PFAS removal, which provides a high rate of diffusion. It's also important to note that both of these products both have lighter density than a typical GAC. And that means that basically it is able to accomplish the same, if not better, performance with less weight. As I mentioned before, GAC will also remove other organic contaminants such as TOC and taste and odor. And this is a point that we know is important to a lot of the municipal folks that might be on the phone, but it reduces the long-term liability by fully destroying the PFAS through reactivation. So let's further discuss reactivation. Evoqua has 3 different reactivation plants nationwide. Darlington, Pennsylvania, and Red Bluff, California are both NSF certified for potable reactivation. And we also have Parker, Arizona, which is our hazardous reactivation plant. And as I mentioned, the largest takeaway for reactivation in regards to PFAS is that the PFAS that's absorbed, as well as the other organic contaminants on that surface, are totally destroyed through this process. And if required, a certificate of destruction is available. All right, and at this point, I'm going to hand it off to Dr. Redding to discuss some testing methods.
Thank you, Caitlin. What I'd like to start off with here are the 2 methods that we recommend when we're looking at how to evaluate a particular application. As Caitlin mentioned earlier, each water is unique. And we see this as particularly important with these compounds. Because they occur at nanogram per liter levels, we're left with a lot of influence from the other background organic matter in the water. So starting with the shortest term approach is the rapid small scale column test. Now this is the only accelerated method that's approved by ASTM. And as it says there on the slide, we can simulate months of runtime within days. This allows us to compare activated carbons. And in particular, it's very useful for comparisons because there is some question as to how well we can really predict performance. One of the caveats there is that the method is only as representative as the water sample used that day. In other words, if the water sample has a lot of variability in it, or the source has a lot of variability, we only know how it's going to perform with that one sample collected that one day. But regardless, if we need to compare activated carbon types, we can use this method. It can be expensive due to the labor costs and analytical costs, but again, it's the quickest way to get to a result where we might want to pick an activated carbon for an application. We can also test different configurations in terms of contact time, etc., but in general, it's just good for selecting an activated carbon. Sorry, jumping ahead there. So the next method, which is considerably more involved, but also results in more robust data, is a pilot test. With this approach, we're able to take columns of media, whether activated carbon or resin, and compare them in the field. By taking this approach, we're able to see what the variation in water quality will, or how the variation in water quality will impact performance, and we're also able to compare carbons side by side. We can accelerate this test to some extent by running a shortened bed depth, but by matching the hydraulic loading rate, But in general, I would expect somewhere between 6 and perhaps as long as 9 to 12 months of runtime before we're going to see breakthrough and have a useful result. This will have about the same analytical costs as an RSSCT and will involve some labor costs, but in most cases it's important to involve the utility in the work, and someone like an operator would sample and then maintain the unit during its life on the site. Again, the takeaway here is that our predictability is considerably better. Now I'd like to cover some of the data that we have for how these various carbons perform in different waters. Here is a unique case where it's a surface water, which we don't see very often for PFAS contamination, but nonetheless, this was the state at this site. What we can see here is that if we have the reagglomerated bituminous material, which is a relatively standard carbon in the marketplace, we can actually exceed the performance of that with our UltraCarb 1240AW, where we're looking at about 45 days of longer operation for PFOA, shown there on the left, and as long as 90 days of additional operation to detection with PFOS on the right. Important thing here to keep in mind is that we have about 3 milligrams per liter of background organic matter, and that does impact the carbon performance. It's almost guaranteed that as the TOC increases, the performance will decrease because of the competition for the sites on the activated carbon. If we look at groundwaters, which are much more typically contaminated with PFAS, we can see an improvement with the enhanced coconut-based product. The enhanced coconut product is one we more typically recommend for slightly lower TOC levels, but in this case, it's quite low. It's about 0.3 milligrams per liter. And we see anywhere from about 40 to 50% improvement over a standard reagglomerated bituminous carbon. To put this in perspective, we're looking at about 60,000 bed volumes to initial detection of PFOA on the left. That's about 420 days of operation. If we look at PFOS on the right, we're looking at about 560 days of operation. And the levels shown here, at least in our experience, are quite typical for groundwaters and the level of contamination. There are cases, however, as shown in this slide, where the levels are considerably higher, where we're approaching actually over or near a part per billion, so 1,000 parts per trillion of these contaminants. In this case, the carbon runtime is decreased simply because we don't have as much capacity for these compounds when we have much higher influent concentrations. But nonetheless, we can take away that the enhanced coconut product with its increased mesoporosity can outperform a standard activated carbon. With the remediation applications, we also have the ability to use other types of activated carbon that may be more economical since we're not producing this water for drinking water. One question that we get asked very frequently is, can I reactivate? As Caitlin mentioned earlier, with the reactivation process, we're able to destroy these compounds. So reactivation is a viable option. Important thing here, and the second question is, if I can reactivate, what's it going to change in terms of performance? What's shown here with the PFOS and PFOA is that we have nearly identical performance for a reactivated enhanced carbon versus its version parent. This is very important economically and also in terms of being able to reuse the material. And we can see that these can perform or quite well outperform a standard coconut-based product and a standard bituminous product. We know from the enhanced coconut product and the fact that it starts out being so microporous that it actually does quite well through several reactivation cycles. The other question is, how long can it be reactivated? It can be reactivated almost indefinitely because there'll be additional makeup added each time, because there is some percentage loss during handling and during due to attrition and particles degrading. And the last question we get asked is, can activated carbon remove short-chain PFAS? It's important to understand what we mean by short-chained. Of course, that's always relative to the other compounds. In this case, we can see that activated carbon can remove down to a compound as short as the pentanoic carboxylate or carboxylic acid. We see that it can remove a host of other compounds, and if we look at this data more closely, we can see that the sulfonates are preferred over the carboxylates. And that the selectivity is pretty important. So the shortest chains of the sulfonates, the perfluorobutane sulfonate, can be removed quite a bit more readily than a carboxylate. And with this cutoff, we can separate out where activated carbon is going to be best applied. A takeaway here also is that you see there's 2 parts per billion of TCE in the mix here, and that during this runtime there's no breakthrough of TCE. So an activated carbon that's applied for general VOC removal or for other targets can also simultaneously remove PFAS. Important here also is the total organic carbon content, which is quite low at 0.2 milligrams per liter, which means that competition with background organics is not too severe in this case. I'd like to turn the presentation over to Kathy Swanson at this time to talk about a resin application.
Adam, thank you so much. So yeah, like Adam said, we're going to change gears a little bit here and talk about ion exchange resin. Now, a lot of people think of ion exchange and they think about a regenerable product. We are not talking about this, and we're not talking about a regeneration process in today's slides. We're talking about a single-use resin. Now, we started looking at this, maybe 10 years ago, and by we, I mean Tom Malman, who's also on the call. But we started looking at this about 10 years ago. And when the UCMR 3 list came out of things that people had to look at in their water, and we said, okay, we know that these substances can be ionic because they're acidic and they dissociate. So what kind of resin might work? And we looked at all kinds of different resins. We looked at acrylic, type 1s, nitrate selective, perchlorate selective. And what we found in our studies is that the perchlorate selective resins theoretically had some of the best characteristics. It's the most hydrophobic. It's got the highest selectivity for PFAS. It's got the longest bed volumes treated. And the advantage is it's a single use. So when you dispose of it at a waste to energy facility, it's burned and the PFAS are destroyed. So we started to think about that. Some of the things, and I'll get back to that story in a sec. Some of the things that we've also found here is that the resin has incredibly long bed lives, and so we'll get into some of the data there. And it's going to sound like a broken record after a while, but the sulfonic acids are preferred over the carboxylic, so that holds true for both carbon and resin. And the other thing that I think is really interesting with regard to this ion exchange is that the PSR2 plus resin is even more selective for PFAS, especially the PFOA and PFOS, than it is for the perchlorate. So let me page down here. Whoops. I don't know why that went 2 slides. Let me go back a sec. All right. All right. So ion exchange, a little bit of basics on what ion exchange is. Essentially, you've got a plastic bead, and it's got little hands on it that are positively charged, and those positive hands are fixed on the resin bead. And it attracts negatively charged anions. And so when it comes in its virgin form, it's got chlorides on it, and so it literally exchanges a chloride for whatever your anion is in the water. PFOA, PFOS, nitrate, sulfate, and as you could see from that chart previously, anything that, as it goes down this slide, it's going to be more and more selective for all of this stuff. So, with regard to PSR2+, what is it? Well, it's an NSF-approved resin. It's used extensively for perchlorate removal. As a matter of fact, in California, Massachusetts, and other places where perchlorate is regulated, it is the most commonly used resin, probably 80% of the perchlorate market it's used in. So the good thing about this is even though it's new, quote unquote, for treating PFAS, it's been used for the past 15, 20 years in drinking water applications for perchlorate removal at a very large scale. So there's a lot of experience with this resin. We talked a little bit about the whole soup of chemicals that encompasses PFAS. It's not just PFOA and PFOS. There's a lot of other chemicals as well. And resin does a great job at picking up some of those, or a lot of those. So we'll get into some of that data. Another nice thing about resin is it has a 2-minute empty bed contact time. Well, what does that mean? Sounds like just a a bunch of acronyms that I'm throwing at you, the EBCT, but really what it means to you is that you can do treatment in a much smaller footprint. We talked a little bit about the large treatment volumes and long throughput, and we'll get into that in some of the data. It's very simple to run. It runs until it's spent, and then you dispose of it. We don't recommend backwashing it anytime, so that is a little bit less equipment as well. And then finally, I touched on this, but when the resin is destroyed, it's sent to a waste-to-energy facility or an incinerator, and they're basically burned and destroyed during that disposal process. So getting back to the story of 10 years ago when we started looking at this, we said, gee, it seems like perchlorate selective resin might be a good idea for PFAS. Well, gosh, there's got to be some sites out there that have both perchlorate and PFAS. And so we started poking around, and what we found, by George, there were sites that had it, and the PSR2 was removing PFAS for a long time. As a matter of fact, it was removing PFAS when perchlorate broke through. You can see the red line here is the perchlorate breakthrough curve. And so basically the system was taken offline. Now this is a full-scale 1,000 GPM, 350 cubic feet resin lead lag system. So, you know, full scale, we see that it's treating, and it's treating well. And so more recently, we've looked at some other sites and said, well, hey, if that was true at that site, what about these others? And we have found consistently that we have had to take the system offline for perchlorate breakthrough before we're really seeing a nice breakthrough curve for the PFAS. So the good thing about that is we know it works really well. The bad thing about it is we don't have a nice breakthrough curve to show you. That said, we have done a number of pilots, and this is a story of one in the West here. So a customer came to us and they said, hey, we're looking for an alternative solution. So they were looking for something besides GAC. And we said, hey, we think this perchlorate selective resin will work for you. And they said, okay, great, but we need to test it. So that's what we did. After 10,000 bed volumes, you can see there was no breakthrough on the PFBS, the PFHXS, or the PFOS. A little bit of breakthrough on the PFOA, pretty low levels there anyway. And basically at 100,000 bed volumes, they said, you know what, 5 months, good enough. We need to put a system in place before the summer. And at this point, there are now 3 systems that are treating drinking water with PFAS for resin around the Peterson Air Force Base. Another pilot that we did, this is an interesting one in that this water had very high TOC. So it really wasn't suited to GAC very well. 14 ppm TOC is very high. As a matter of fact, it turned the resin black within the first day. But what's amazing is that you're still seeing really good removal. And you can see no breakthrough up to 150,000 bed volumes on the PFOS and the PFHXS. You did see the PFOA breaking through. Again, lower levels, and it keeps it all below the health advisory levels. Moving on to the next slide. So when I talk about Gen X, I am actually not talking about a generation of people born between 1964 and 1985, or however you define Gen X. Gen X was actually the replacement chemical for the some of the PFAS materials that was supposed to be safer. In any case, we have done studies. I'm not at liberty to share those results right now, but what we are seeing is resin is showing good removal capabilities with the Gen X and some of the perfluoro ethers. Some of the other things with these types of chemicals is, you know, like I said, broken record. The sulfonics are absorbed better than the carboxylic acids, and short chains, well, long chains are preferred over short chains. And then this is a pilot that we're doing here in California. It's also treating perchlorate at this site, but you can see we're out to 100,000 bed volumes. And really, all of these chemicals down here were at zero breakthrough. So just a really nice story of what resin is able to provide here. I mean, bottom line, each water is unique. Everybody has different considerations. I think some of the things to think about when you're trying to decide what technology, look at footprint, look at if you're going to use it seasonally, look at if you're treating surface water or groundwater. What other impurities do you have in the water? What are the TOC levels? What are the competing ions? All of these things go into really making, you know, the most cost-effective solution for you, and we're here to help. So with that, I thank you for your attention. I'm going to turn it back to John.
Thank you, Kathy. And I appreciate everyone's attention. Just in closing, before we go to the Q&A, at Evoqua, we provide sustainable, safe, and environmentally friendly solutions for communities and the environment. We have national coverage with our branch service network, so Evoqua can reach big cities and small towns within a 2-hour drive. Evoqua also offers easy financing options for your project with lease-to-own, rental, capital purchase, and build-own-operate solutions. I want to thank you for your time and participation in today's webinar. We will now start the question and answer portion of the webinar. Steve with WEF has been compiling the first questions. Stephen?
Thanks, John. So the first question that we have is, I believe, for Caitlin. In what scenarios would ion exchange be a good fit?
Sure. We help our customers to answer that question every day. Every water is certainly different, so we would recommend testing if you're looking at multiple technologies. But if you're looking at ion exchange or GAC for that matter, you know, there are two different parameters that you could look at. It could really boil down to. The first is, you know, is there something else that the customer wants to remove? And so, for example, are there other organics in the water that GAC could also remove? Or is there, for example, maybe perchlorate in the water that you'd want to look at ion exchange to help you remove that as well? And then secondly, what could be impeding that performance that's in the water? In the example of GAC, we've talked about TOC being a competition for those PFAS absorption sites. If it's a high TOC water, you're going to want to look at considering resin. If it's, for example, water with high TDS, you're going to have more competition for the ion exchange sites. So you might want to look at GAC in that situation.
Okay, thanks. The next question, how do the costs compare between carbon and resin?
Hi, this is Tom Allman. My chance to speak now. Costs vary depending on how you look at them. The first aspect is clearly the capital installation. The capital for carbon is higher because it has much higher empty bed contact time than resin. 2 minutes for resin, 7 to 10 minutes for carbon. As a result, we either need more vessels for carbon or we need a larger vessels for carbon, depending on the flows. And what we find then is that we have much smaller footprint with resin, probably half the size, and capital is about probably 2/3 of the cost of carbon. The other aspect is the cost of the media themselves. Resin is more expensive than carbon. There's no doubt about that. It also gets more throughput. So it's just not a matter of what are your dollars per pound or dollars per cubic foot. It really comes down to what are your dollars per acre foot. And rule of thumb, they are probably somewhat close, and there's a lot of variability there because, as Caitlin and others have pointed out, interferences are not the same for the both of them. And frankly, what you run into is that in one case, carbon may be the more economical solution, and others, resin may be.
Okay, thank you. Another question we have, this is John Lombardo. Although we've seen increased performance with the GAC products, does it also come at an increased price? Adam Redding, Dr. Redding, would you like to field that, please?
Yeah, sure. The short answer is yes. What it has to come down to, though, is the performance. If the performance is high enough to justify the cost, that's the easy answer. Really, the other costs to consider in there is not just the media itself, but the cost of an actual change out. So if you can decrease the number of change outs in a set period of time, certainly you can decrease the overall cost. There are other carbon products that can work fine, but really in this case where the consumer in a lot of cases is asking, can I have non-detect as my treatment goal, the increased cost is often worth it.
Excellent, thank you. Another question that came in is, what is the cost difference between virgin and reactivated GAC? I'll go ahead and answer this one. The cost difference on average is about 70%. So going with reactivated carbon will typically save you about 70% of the cost of virgin carbon as a general rule. Next question, I'm working with a couple of different communities that are discovering they have this problem. I assume PFAS is the problem. What should be their next step? I'll go ahead and answer that one. First thing would be is to, if you're a community and you're dealing with this, you need to contact, or I recommend that you contact some type of engineering or consulting if that's what's in line. Another thing would be to contact a supplier like Evoqua to get in and help maybe direct some of that and provide information for guiding in the right direction, and maybe to work with your engineering company. There's a lot that's involved in that, geological studies, other things along that need to get done to make sure you're curing the problem. So that would really be the first step, is to make sure you have some experts on board to make sure they can guide you to the right solution. Next question is, what is the typical process for these projects from discovery to installation? I'll go ahead and take that as well. It's similar to the one that was just asked. I would say typically once it's been discovered, communities usually reach out to some type of engineering company to do studies, groundwater studies, to find out where the source is, and many other things along those lines. And then from there, they bring in other people, usually solutions providers such as Evoqua, to assist them with the process of scope, sizing, other things along those lines, budget, so that the communities or corporations can go ahead and get funding or set aside money for cleanup or treatment on an ongoing basis. Next question. I have a site that has PFHXA. What would you recommend, GAC or IX, and why would you recommend it? Adam, Tom, I think this will be a combination for you guys. So if you want to go ahead and answer.
Yeah, I'll take first crack at that and let Tom follow up. The PFHXA, the hexanoic carboxylate, is really the tipping point where GAC becomes less economical. So in other words, as I mentioned before, because it's not just the chain length, it's also the functional group that's going to be important. If that were the sulfonate, not a problem, but because it's the carboxylate and the chain is starting to get shorter, so we're one carbon less than PFOA, it becomes challenging for carbon. And it's going to be, if it's in the mix, the customer wants to remove it 100%. I'm probably going to shy away from carbon and say, okay, if you had the heptanoic acid with one more carbon in the chain, okay, GAC is your fit. But I think Tom can talk about the ion exchange challenge for that.
Sure, I'll take it from here. You're right. It's certainly one of the shorter chains, and it's actually more difficult for both resin and carbon to remove it than PFOA, which is significantly longer. As far as experience, I think the things we've talked about what the interferences are, really matter. When treating surface water, we've seen probably around 8 times throughput of resin than over carbon. So whereas we had a short throughput on carbon. Certainly we had 8 times that throughput for resin, and certainly that would be the tipping point of saying certainly that is far more economical. At another site where it was groundwater that was relatively clean as far as TOC goes, but fairly high in sulfate and TDS, certainly we had a lot of interference there, and we were looking at only 3 times better for carbon over resin, or I mean resin over carbon, in which case that may throw the tipping point somewhere else towards carbon, simply because there's a lot more interference for the ion exchange with a high salt background. Back to you, John.
So I guess what we're saying in general is it's still going to come down to the water quality, but we'd have to think about it more. Okay. All right, John.
Thank you, Adam and Tom. Yes. I have another. We looks like about 4 minutes left here on time, so we'll get another couple questions in. What is the expected change-out frequencies for GAC and IX, or what is the throughput, and how long does the media last? So Adam and Tom, I'll throw this back to you guys.
Tom, do you want to go first?
Sure, I'll go first. Resin life is fairly long. We typically size somewhere in the range of 6 months to 18 months bed life, and that's usually lead lag, and the lead bed gets exchanged out every 6 to 18 months. And so that's our typical life that we've been seeing on perchlorate, and for design purposes, that's what we're expecting for PFAS.
Okay, for carbon, like the first case that I presented with the surface water, we're looking at 20,000 bed volumes, a 13-minute contact time. That equates to 180 days. I think that's fairly good. What I would like to see, just as my rule of thumb, is about 9 months of operation, of runtime, to where I really feel like it gets to be economical. To look at that second slide in the mix, which showed a groundwater with not a lot of competition for the carbon, there where we were well over a year, we were at 420 to 560 days. That I feel certainly would be economical. I mean, this question really is the million-dollar question, and it gets back to why we discussed the RSSCT and pilot testing. Almost everything has to be couched in what's the water quality, and these compounds are definitely difficult to estimate. From the ion exchange side, we have a model that Tom could speak to. GAC, we're still working on anything close to that. So again, the million-dollar question, but I'd like to see longer than 9 months, and certainly we can hit that in just about every case.
Excellent. Thank you, Adam and Tom. Another question: how many times can carbon be reactivated before it affects performance? Adam, I'll toss this one back to you.
Yeah, I had mentioned that one in the presentation, but what it comes down to is that with each cycle of reactivation, there is some percentage of makeup with virgin carbon. That makeup is added because in the handling, the slurring of the carbon in the kiln itself, the particles abrade. So there's some mass loss as dust and particles smaller than the smallest fraction of the carbon. So with a soft activated carbon, soft would be on the end towards the sub-bituminous product. The makeup may be 15%, maybe as high as 20%. With a harder activated carbon, and this is one of the benefits of the enhanced coconut product, the makeup is down on the end of, say, 5%, 10%. So this is very important, but in short, it can be reactivated almost indefinitely because there's a point there after 7 to 10 cycles that the original material is gone and it's now just been replaced with makeup that's also seeing cycles.
Excellent. Thank you, Adam. I think we're coming up on 1:45, so I think we'll take maybe 1 or 2 more questions. Another question I have, so state requirements were below the EPA standards and thus more stringent. Caitlin, would you like to answer that one, please? So it's state requirements were below the EPA standards and thus more stringent.
Yeah, state requirements are going to vary from I think there's about 12 or 13 states that now have regulations in place, and they varied from as much as meeting the EPA's health advisory limits to including a larger array of PFAS to also having a limit that's much lower than that 70 ppt limit that the EPA has set. And oftentimes as well, I mean, as I mentioned previously, even in lieu of these regulations, public perception is really the driving factor. Even in states that have regulations in place, we've seen the target treatment goals to be as low as non-detect, oftentimes because of that public perception factor. And so it's an interesting environmental issue when you're not really looking at the regulation that's typically the driver, but really trying to take it out in entirety.
Okay, thank you, Caitlin. This will be the last question because I think we're actually about a minute over, but we'll get in one more. And I think this one, Kathy, will be for you. Are you suggesting PSR2 Plus would be a good drinking water treatment candidate if high nitrate and trace PFAS? PFAS, I'm sorry. If high nitrate and trace PFAS.
Well, I guess, what does high nitrate mean, right? I mean, if there's high nitrates in the water, they are competing. And it's interesting because you've got ppm of nitrate and parts per trillion of PFAS for the most part. If you're under drinking water standards for nitrate, then yeah, the PSR2 Plus is going to work really well for PFAS uptake. If you want one resin that's going to treat nitrate and PFAS, we may want to talk about that. You know, get us some water quality and we're happy to continue the conversation.
Excellent, excellent, thank you. I think that's about all the time we have, Stephen. For those of you still on, we do have information up on the screen now. You can email your questions or phone them in. I know that we will compile the list of questions that you've submitted. Our apologies, we can't get to all of them. There are certainly a bunch, but we will get them listed, and one of us will make sure we get back to you. So Stephen, if you want to take it over from here, please.
All right, we just want to thank everybody for attending today, and please look for the follow-up email that'll come out in about 24 hours that will have the link to the webcast recording as well as the PDF handouts. Thank you very much. Have a good day.